It is interesting to consider the proposed model at very early epochs in the development of the universe. If we go back far enough in time, the effect of gravity becomes so great that it would take a lot less mass even to form a star. The effect on stellar evolution is rather dramatic. For example, you can go back and if you follow this relationship where the gravity goes up like this, we get closer and closer to the beginning of time. Objects, for example, the size of Jupiter, for example, could actually become a star. Well, if this is indeed the case, if we look at very distant galaxies, there should be evidence of this very high prolific rate of stellar evolution. In fact, if stars become, let's say, the size of Jupiter, they would evolve very quickly because it wouldn't take very much time for them to consume their fuel, collapse, go through a collapse and explosion, and spread their contents within their solar system. So there should be observational evidence of this. Well, it's interesting. When we started looking, now normally it would take for a star to evolve and live out a lifetime. We're looking at billions of years. Let's say our sun, it's going to take another 4 billion years before it goes through its process. So if the stars are more massive, they'll evolve more quickly. But there's a limit to how much this mass, how big these stars can get to get unstable, and we see a typical range of sizes for stars. But so if we start going back in time, we should see stars in galaxies that have not, if you keep with the standard model, we should see stars, excuse me, that have not had enough time for them to fully evolve and go through their process, then explode and distribute the new elements that are a result of this solar fusion. You get the elements like iron and oxygen and nitrogen, all these elements that are all heavier than lithium. Astronomers call these stars that are produced, and of course, as a result of a star living out its lifetime, metals. Anything higher than lithium is considered a metal. And then, so when we look at it very early in the universe, stars should not have had enough time. You're looking less than 1 billion years. And the stars should not have had enough time to fully evolve, live out a lifetime, explode, and produce the metals. Well, it was kind of a surprise when we looked farther and farther back in time, and we see within very young galaxies evidence of metals. Now, not as much as we see in our present universe, but where did these metals come from? How could they possibly exist? So what astronomers did is they came up with an after-the-fact solution. What they said, well, during this very early age of the universe, there must have been these special type 3 stars. Now, we've never seen them. In fact, there's some physicists who have determined that they can't possibly exist because they're too unstable. But if the star is big enough, you could, and has enough effective gravity, but the bigger it is, the more pressure, the more quickly the stars would evolve. In this very early stage of development of the universe, these big stars would generate enough, would live out their lifetime fast enough to produce these elements that we see in these very young galaxies. So, but in the proposed model, rather than an after-the-fact solution, this kind of evidence of metals being produced very early in the universe would be expected. Stars the size not much bigger than Jupiter itself will have lived out an entire lifetime, gone through their lifetime, exploded, spread out their contents across the universe within their solar system, and we should see this. In fact, what's interesting to note is that, let's say within our solar system, or a system of planets the size of our solar system, if in which there was let's say one primary star and several smaller planet-sized stars, if one of these were to evolve and then blow up, it would cause a chain reaction, a boom, one to the next, to the next, to the next. And you should see a series, a kind of seismic kind of variation in energy output. And what's interesting is this is exactly what we see when we look at quasars. Quasars are really far away. They have a very high redshift, and they were not expected. And then we see, geez, these things put out roughly, let's say 100 to 1,000 times the amount of energy you see in a typical galaxy. So these are very early galaxies, and some sort of idea or solution had to be proposed to explain the energy output of these quasars. So what was proposed is that we put a supermassive black hole, and as matter comes crashing into the gravitational reaction, the matter would run into each other like a mass of people all trying to get through one door. And as they bump into each other, they generate a certain amount of heat. Well, this kind of intense energy output is what was the after-the-fact prediction to explain the energy output from quasars. Well, maybe that you could still keep that model if you want, but the proposed model, it says you don't really need to resort to that after-the-fact solution. What you're looking is just accelerated stellar physics occurring. So, and there's more evidence of this accelerated stellar physics, and it gets particularly interesting when you consider our own solar system, which will be discussed in the next video. Thank you for your time.